Falk Meyer from Breach Steps for the second to last talk from today, and it's about hardware, debug ports, acceleration, JTAG interfaces. I'm really looking forward to it. Thank you for being here, and please give a warm welcome to Falk.
All right, hi. So as you can see, today we are presenting as SciQT/Breach Labs, right? And dissecto is also involved to a certain degree. I think the main thing we can take from this talk today is to see that in this industry, we really need to share a little bit of information every once in a while in order to discover new approaches. And I want to introduce you to a little bit of how you connect to a JTAG port on an automotive unit, or in general to a JTAG port. And especially without very expensive debugging equipment, because as you're probably aware, whenever you start and you go into the depths of sourcing different sorts of statements and offers from vendors, for example, from iSystems, so you take a look at the Lauterbach, right? You get offers, and they are somewhere in the tens of thousands, and you have to purchase for every different architecture that you are taking a look at. Again, so basically, this is why we're going to take a look at this today. A little bit about myself. As I already mentioned, I'm from Breach Labs. We focus on automotive penetration testing, and we have a couple of great colleagues here today. I think the crowd is actually way more technical than I expected it to be, so congratulations on the hosts. So today I'm speaking to you in my role as a sort of independent expert from the SciQT. But let's jump right into the topic. I'm familiar, everybody knows JTAG in general, right? Fantastic, all right. So in general, the JTAG protocol is defined in the IEEE standard 1149.1, right? And it's usually used to debug your software, to transfer data from non-volatile memory, to output data onto the controller, to monitor what's going on, right? To debug during the development process, and also to have static fault and signal state testing. But how does it actually work? So technically, one of the methods you can use JTAG is called boundary scan, and this is what we're going to take a look at today. In general, we're going to take a look, and every JTAG device that you take a look at has one or more TAP controllers, right? And TAP stands for Test Access Point. And at the end of the day, TAP is a finite state machine, right? That's controlled just by transitions within the state machine, and two different sorts of register that we're going to take a look at, an instruction register and a data register, right? Okay, you can interrupt me at any point if you have any questions, right? Because the idea of this talk is sort of to demystify a little bit of what happens with a JTAG. All right, so TAP is connected basically with 4, sometimes 5 different ports. You have your test data input. This is where the data is basically transmitted from the tester into the chip. You have the test data output, which is where you read your information back from, that is outputted by the chip. You have your clock in order to sample the data, either on the rising edge or on the falling edge. And you have your test mode select. The test mode select is exactly what we took a look at earlier, where we transition basically through the state machine of the TAP controller. Sometimes you also encounter a test reset, right, which is the reset signal for the state machine. Here we have a small example of the state machine, right? You can see, for example, we have the clock, and we have blue and we have red lines. You can see that TDI is always sampled on the rising edge, basically, while TDO is sampled on the falling edge of the clock. And this is basically how you can imagine this. And then we can directly jump into how it works. So we have, as I already mentioned, we have 2 different registers. We have the instruction register and the data register. And what the instruction register, as the name suggests, stores the current instruction you want to execute. While the data register is basically a placeholder for the registers that you want to have on the chip, right? Then we have 3 different types of main types of data registers. There are more, right? We won't go into too much of detail. So we have the boundary scan register, the bypass register, and the ID code register. And today, I think we stole this from a very nice website. If you want to give credits to the guy, the link is below. Fantastic article on JTAG, in case anybody's interested. And what you can see here, for example, on the left, we have TDI. On the right, we have the TDO, which is where the data comes out. And then you can see, depending on basically which type of value we have loaded into our instruction register, we choose a different sort of switch, right? And this is basically what the switch 1 and what the switch 2 do. And then you can specify which data register you want to have, which is switch 3 and switch 4. We will go through this in a little bit more detail, but in general, this is what we are trying to see. If this concept is kind of clear, we can see that how do we actually transfer data from TDI to TDO? How do we extract it from the chip? And this is done by using shift registers. Shift registers can be imagined fairly easy. It's a sequential register where you shift bit by bit, right, 1 per clock cycle. And then the bits get pushed in from TDI and they get outputted by TDO, 1 per clock cycle. What we are trying to find today, for example, is the ID code, right, which is a unique identifier of the device. If your JTAG is open and it is accessible, it's very likely that you can send an ID code command, which is also documented in some other files, which we will see later. But it's comprised of the version number, the part number, the manufacturer ID, and then a bit. Right? This is basically to give you a little bit more information that you're dealing with the right tab on the device, because there can be, again, multiple tab controllers, and you want to identify which ones you're specifically targeting, and if the ID code command is implemented as you said. Then we have the bypass command. The bypass is basically, as the name already suggests, you signal to this tab controller that you want to skip it, right? This is why it's a 1-bit instruction. Right, so you basically don't want to include it into the scan chain, into the JTAG chain, and this is exactly why you do that with sort of chips that you know that they are locked, they don't support your JTAG instruction, or you're simply not interested in them. And then we have the sample and preload instructions, which can close the loop between TDI and TDO and directly output the signals that are currently on a selected pin. All right, then we have the state machine. The state machine is actually a crucial thing if you deal with JTAG and you don't want to use, for example, a debugger that you can use via a graphical user interface. And each state is basically a combination of the signal values that you have on your TMS, so your test mode select and your test data in. And the transition between the states are always sampled from the TMS signal, right, on the rising edge of the clock. Here we have a nice example of how this looks. You can see on the top left we have the test logic reset, and those little values that you can probably hardly read from the back are basically the values of TMS on a rising clock cycle. You can see basically test logic reset means we don't have any testing activated. This is in a default state. Then we can transition towards the one test idle. This is where all of those things are initialized. And then we can transition either into the select data register scan or into the select instruction register scan. So this whole chain, that looks very similar to this chain on purpose, is the instruction register chain, and this is the data register chain. So basically, whenever we want to perform a certain instruction, we have to put the instruction register or the data register into a certain state, right? And then push the data into TDI and read the data from TDO depending on the current state that our JTAG is in. Here we have an example, right? You can see once we go from the data register scan to the instruction register scan, this is where the switch 1 and the switch 2 of the picture we have shown earlier change. All right, and here we have basically another example. Once we have seen, okay, the top ones, they basically select if we want to choose the data register or if we want to choose the instruction register. But what happens if we go from our data register scan, right? We have our TMS at the logic level 0. Then we go into the capture data register state. this is where the current state, right, internally is loaded into the shift register. So technically we are reading from some register that is on the device itself. We are reading the value and pushing it into the shift register so that we can read it out. Then in the next step we have the shift data register. This is where we, as described, push data from TDI to TDO in order for the bits that we have just copied into the data register to get outputted, and we can read them. Then we basically transition from there, and we just say, okay, we can also update, and this is basically the reverse operation of the loading that we had just had. All right, now we come to the application, right? And JTAG is fairly standardized when it comes to the processor architectures, but every processor architecture has some nuances, and sometimes very difficult to determine how it works, right? And there's a big difference between security testing and penetration testing, right? It was pointed out multiple times today as well. And we're going to focus today on literally just security testing, because the more we automate security testing, the faster we can come to the fun part, where we actually try to exploit something. So if we just want to check, for example, is my JTAG interface locked, right? How do we do that without spending multiple tens of thousands on a debugger every year? And this is basically also what got us a little bit into researching the topic a little bit more, right? We reached out and we talked with dissecto a little bit, and we also said, there might be a better solution. And they were like, yeah, why don't you just copy over what the expensive debugger does and write it into a script, and then you can run it every time, right? But in order to understand what's exactly happening, this is how this presentation basically came up. All right, so we can, for example, take a sample instruction, which is the ID code, and then we can see, does it return a valid result, right? Or are we completely locked out of the interface? And for example, if the instruction doesn't return any value, or if it returns like false values, right, that don't match the specification that we have read, for example, in the data sheet, as you can see here, then the JTAG interface is probably not available. In order to understand a little bit better, maybe you have those files available. When you read about debugging, there are a lot of nice graphical user interfaces, right? And they usually require you to upload a BSD file, right? BSD stands for Boundary Scan Description and then language, right, to complete the BSDL. And the main function of those files are to give you the pin configuration for which pins on the board actually support JTAG. We're going to take a look at that in a second. And basically, it's usually provided by the manufacturer in order to help you to automate those types of tests. I won't go into those in detail just now, but on an example. So if we take a look at the BSDL file, there we go. At first, we have our entity description. An entity description always starts with the type of controller we are taking a look at, and then basically ends with the end statement at the end of the day, which we will see on the second slide. And everything else can be either contained outside of this entity declaration or it is inside. In this case, it's inside. So there we have the generic parameter, which is basically the type of package. If you have multiple chips in different packages, it's very important to understand how the pins are configured. This is also here. And then we come to the logical port description, right? This basically describes how this pin map that we have just described by having the generic parameter is mapped out on the pin itself. Then we have the different use statements and the pin mappings down here. Here you can see, for example, we have a tap scan clock, which is here declared as JTCK. Right, it runs at 10 megahertz, and it's both on the rising clock edge and on the falling clock edge. Then we can see that on this specific chip, the TDI, the TMS, TDO, and T reset are all true. I will quickly run over those. Those are not that important. But this actually gives you one piece of information that is very crucial. You can determine this experimentally. And I'll quickly ask you in a second how you would do that. But for example, this is one thing you would have to keep in mind, the instruction register length. You have to have the correct instruction register length when you talk to a chip in order to determine, in order to actually get some feedback. Okay, there we go. Quick overview. Now, as I already mentioned, we want to get this done as quickly as possible, right? So we just want to connect and get this out of the way. And this is basically what the test case we have envisioned, right? We want to send to the JTAG interface an ID code instruction, and we see if the ID code instruction is available on the target device. So we connect to the pins, we power on the device, the test case instructor would send the ID code instruction, and then compare the result that you have received with the result that you have expected, for example, from the datasheet. Well, and this is exactly what we do, right? In the basically also with a HydraProbe. This is where dissecto comes in again. You can define your own test case, right? And they have an RP2040 microcontroller on there, which allows you in order to write a little bit of MicroPython code and to sample all of those things. So this is, for example, one of the specific functions that you can take a look, right? If you ask Niels very nicely, he will share the test case with you. We basically turn on the power supply, right? We wait for a little bit for everything to initialize, and then we run the ID code test, right? Seems fairly straightforward, and this is pretty much all you have to take care about if you have defined all of your parameters accordingly. And we can also take a look at this in a little bit more detail, but at the end of the day, what it does is it calls this transact data register function with the bits, right? And then pushes out the ID code command based on what we have done, and then basically dissects it into the right parts and prints them out on the console. Wait, one sec. There we go. And this is basically this function, right? At the end of the day, all it does, this JTAG TRX function, it's actually very interesting because you are in control of the clock, so you can tell how fast it runs. Therefore, you can basically say, okay, I set my clock to a logical value of 0. Then I set my TMS value to what I want my state machine to be in. I set my input value to what I want to have, and then I set it to 2 again, right? So I have performed basically one clock cycle, well, half a clock cycle to a certain degree, and this is exactly what I'm doing here. You remember the state machine? We basically transition from the idle state, we have just initialized the logic, to the data register scan, right? But and if we want to have the instruction register, this is where we go in here. And then we can basically just run through the same thing that we have done earlier. All right, sorry, that must have got in there. All right, any ideas based on what we have just talked about on how you could determine the length of the instruction register without having a BSDL file available? Yeah.
Bypass instruction and then pop through how long it is to return to itself.
Yeah, pretty much, right? I mean, you can just push a lot of values basically into your data register and then basically wait until and count the amount of clock cycles. Perfectly right. And how do you determine how many tap controllers you have? It's a very similar approach. You basically do the exact same thing, right? So you collect basically, you set all of them, set ones in your instruction register, then you set zeros in your data register, and basically push as many in as you possibly can in order to reset all of the different tap controllers on the line, and then you push in a 1, and then count the amount of clock cycles until the 1 comes out on the other side. This is how you determine the amount of tap controllers. Any questions to that? I want to keep this short and sweet because I know we're going towards the end of the day. So thank you for your attention. And if there are any more questions, please let me know.
If you were to pen test the JTAG interface, what tooling would you recommend?
Depends on what you have available, to be very honest, right? If you have very fancy equipment available, please feel free. It also depends on the scope that you have available. If you, for example, say, I just want to check if my debug interface is logged, you can again use something very simple, like for example on the HydraProbe at the moment, right? You can basically use any sort of controller that you want because you just set logic levels at the end of the day. If you want to say, I want to also later perform further sort of instructions, I want to dump the memory and so on, this is where you can either look into OpenOCD if it's supported, or you can go into fancier tools like, for example, the Lauterbach or the ICE systems.
Thanks.
Thank you for your presentation. I have a quick question. I've noticed that a lot of the time the JTAG is not completely locked, but password protected.
Mm-hmm.
Is there, like, my question basically two parts. Does this ID code thing tell you if it's password protected, or is there a generic way to detect this?
I don't think there's a generic way to detect that, right? Basically, the command would simply fail, as we have just described. So in that sense, it's not completely locked, but it is password protected. We have not determined a generic way just yet. If you have any ideas, I'm happy to discuss them.
No, I have no ideas.
Basically, just ask your customer at this point.
Yeah, so you said also before it's pen testing and security testing, right? So
yeah.
What kind of security testing actually, like, how do you differentiate here between, like, what would be, yeah, if it's locked or not, that's one point, but let's say it's locked, but then what would be the next part? You know, like, what kind of list of test cases you can do, or, you know?
Yeah, I think that's perfectly reasonable. So I would usually start, before you start the penetration test, you start with an amount of research on certain vulnerabilities, right? I think we're all quite aware, and I know that some of our customers in this room are still using TC2 controllers, for example, with the existing JTAG vulnerability that is, for example, just read after a certain period of time. So you have a certain amount of time after boot in order to dump the memory. Right, this is why Infineon issued the patch for it, that you should protect your P-flash, for example, with a password, or encrypt it entirely in order to prevent somebody that has dumped the firmware to do anything with it, like William has shown earlier. Right, and the second thing is basically also based on the same mechanism. Usually when the device boots up, for example, on ARM architecture, there's a certain ARB code, I think, register. It's red. It's sort of a flag if the debug interface should be locked, right? And this is where the beauty of fault injection again comes in. If you are able to determine the exact timing after boot, this is how you can then bypass, for example, that this register is correctly set. Please.
Thanks, really nice talk. Is there a similar easy approach for SWD?
For SWD, it's a fairly straightforward approach as well. It's basically also try to send some generic commands and see if you get a response. Yeah, it can also be implemented in the same fashion. All right.
Thank you again for your talk.